Thank you, Graham, and thank you to the rest of the committee. I'm deeply honored to be giving the Omega Rho lecture. Also, when I was in college, I never joined a fraternity, so it's nice to finally be part of the Greek system. I actually have to find, oh, here we go. So, oh, there. Okay. So I'm going to give a broad but shallow talk today on these 5 topics. However, all of the papers related to these papers are on my website, so if you want more details, you can find them there. So I plan to spend about 10 minutes on each of these topics, kind of briefly motivating the problem, giving you a kind of a hint of what the model is, giving you the main numerical results, and talking briefly about the potential impact. So we have one problem that's kind of a classic problem on allocating blood for transfusions, 2 kind of newer problems that are about height and weight of children at both extremes, obesity and undernutrition, and then 2 problems that are essentially biometric problems. That would be ballistic imaging and the universal identification program that India is currently undertaking. So there's a few common themes here. First and foremost, all of these problems are public policy problems. Each of them, there's a large longitudinal data set that for most of them is really used to guide the modeling. This is not so-called big data. I don't know if there's a word for like medium data or small data, but this would more fit there. And for each of the problems, there's an existing policy that's being used, and so we come up with our proposed policies and compare them, and I'll show you usually trade-off curves. For the health-related problems, it'll be health versus cost. For the other biometric problems, it'll usually be detection probability against false positive probability. Okay, so let's jump in. First problem, blood transfusions. This paper appeared in the flagship journal of that field, which is called Transfusion, last year, joint with Mike Atkinson, who's a former Stanford PhD student, and also 2 Stanford Medical School faculty. Okay, so a little background. 5 million people per year in this country get a blood transfusion. And the motivation for this work is that it's recently been shown that the risk of bad things, even death, occurring has an association with the age of the transfused blood. So by that, I don't mean the age of the donor. I mean on the horizontal axis, on the horizontal axis here, it's the time that elapses between when you take the blood out of the donor and you put it into the recipient. And the vertical axis here is just the probability of something bad happening. So a little more background. Blood is thrown away after 42 days. The current policy is essentially a FIFO policy. So suppose you had a patient with A positive blood type, then what you would do is first look for an exact match, and among all the A positive blood you have, you would give the oldest blood, so it's first in, first out, and if you don't have any of that blood, then you'd go to this compatibility matrix. And so here you'd see that for A positive patients, there's 3 other blood types they could get. And so among those compatible blood, we would give the blood with that's oldest. A key factor here is what's called the supply to demand ratio. And nationally, there's excess supply, but this varies from place to place. Okay, so the main research question here, is there a better allocation policy than FIFO? And our approach is really to keep it simple. So we're going to look at a 1-parameter policy, and our longitudinal data set is 1 year's worth of blood transfusions, so 19,000 transfusions at the Stanford Medical Center. And I'm not going to take you through this slide, but if you just do some simple accounting, you can see that minimizing the number of outdates, that is, minimizing the amount of blood you discard after 42 days, is equivalent to minimizing what we call the imports. So if you actually have someone that you have to give an operation to, and there's no blood available, you don't just let them bleed on the operating table, you import blood, and of course that's going to be expensive, but that's what's done. So of the two, we can just choose one of those. We're going to choose the import rate as a constraint, and we're going to minimize the mean age of the transfused blood, again, going back to that graph from the New England Journal of Medicine paper, which I had nothing to do with that paper. Okay, so this is a queuing model. You know, think of the donations of blood as being the arrivals to the queuing systems and the transfusions of being the service process. Okay, so this is maybe the most important slide. So this is our policy, and as far as I know, it's a new policy, but if anyone has seen this before, please let me know. Don't let me know now so you don't embarrass me in front of all these people, but you know, email me later. So we have a single parameter tau, which is measured, it's an integer measured in days from some number between 0 and 42 days. Like the existing policy, we're only going to throw away blood when it hits 42 days. And like the existing policy, we're going to focus first on an exact match and then look at a compatible match after that. So again, let's assume we have an A positive patient. So we're going to first look at our A positive blood. And for concreteness, let's just choose a value of tau, say 14 days. So what we're going to do first is look for A positive blood, look for the oldest blood that's younger than 14 days. So we look for 13-day-old blood, there isn't any. Look for 12-day-old blood, there isn't any. We find some 11-day-old blood, and we transfuse that. If there's no blood younger than 14 days, then we go to, we look at the youngest blood older than 14 days. So we look for 15-day-old blood, we don't have that. 16-day-olds, we don't have that. Oh, there's some 17-day-old blood, and so we transfuse that. And then if we don't have A positive blood, we do the same thing again, but with the compatible blood. And so this class of policies really provides a continuum from LIFO to FIFO. So if you set tau equals 0, this is LIFO, and if you set tau equal 42 days, this is FIFO. Okay, so here's our main results. I imagine in the back you can't really see that. Actually, can you hear me way back there? Can someone wave? Okay, good, thanks. Okay, so the vertical axis here is the mean age of the transfused blood. So we want that small so we can get better health outcomes. The horizontal axis is the fraction of blood that's imported. We want that small so we don't spend too much money. So we want to live near the origin here. So let's look at a particular curve, say this red one right here. So this curve is generated by varying the value of tau from 0 to 42 days. So the top left part of the curve corresponds to FIFO. The bottom right part of the curve corresponds to LIFO. And there's a whole bunch of curves here, and each curve corresponds to different values of the supply to demand ratio. So what we really have here is a phase transition. So there's other areas of applied math, say random graphs, icing models in statistical physics, mathematical epidemiology models. They all have phase transitions, but some of our models do too, including queuing models. So what's going on here is that when supply is less than demand, these curves are essentially horizontal. And so because we want to live near the origin, you'd want to live to the left of that curve and use FIFO. And once the supply gets bigger than demand, these curves get vertical. And it's hard to see, but there's a whole bunch of, like 5 or 6 of these curves that are just piled on top of each other here. And so then you want to live on the bottom of the curve, and that corresponds to LIFO. And the interesting thing from a practical point of view here is that the phase transition is exactly where the action is here. So New York City, the supply is less than the demand. For our data at Stanford Medical Center, supply was, the ratio was 0.99, so it was slightly less. In Minnesota here, I imagine there's excess supply. The average excess supply in the country is something like 8%. And so the punchline of this paper is that if supply is less than demand, if supply is less than demand, like it is in New York City, keep using FIFO, but if supply is bigger than demand, like it might be in Oklahoma, switch over to using LIFO. And so this requires a cultural shift from minimizing outdates, which is what these people who run the system think about, to transfusing fresher blood. And I've had phone conversations with the chief medical officer of the American Red Cross, and it takes me a while to get them to internalize the fact that if you have 8% excess blood, you're going to throw away 8% of the blood regardless. And so you may as well transfuse fresher blood so you can save some lives. And because there's so many people receiving blood transfusions, our estimate of the number of people who would not die within 1 year of a transfusion is a very conservative estimate. It's like 20,000 per year. Probably our best point estimate is more like 50,000 per year. So as far as next steps, so there's 2 large randomized clinical trials going on that I have nothing to do with, that are trying to confirm the results in the New England Journal paper, and those will be done in a couple of years. And in the meantime, we've contacted the authors of the New England Journal paper who are at the Cleveland Clinic, and we've modeled their supply chain. It turns out Stanford is a centralized supply chain. They own their own blood bank. They own their own blood center, and here Cleveland Clinic gets their blood from American Red Cross. So in this case, when you have 2 players in the supply chain, it's the upstream players, that is the American Red Cross, who really has leverage in the system. So they're the ones that really have to use LIFO. And so we're actually running a 6-month trial, which is supposed to start December 1st at the Cleveland Clinic with the American Red Cross. And they're going to switch on December 1st from FIFO to LIFO, and we're going to measure the impact on the supply chain. And the hope is that in a few years, if these results confirm, the new clinical trial results confirm the original New England Journal paper results, that we'll be in a good position, really, with the Cleveland Clinic leading the way to kind of make a transition from FIFO to something towards LIFO. Okay, next topic, childhood obesity. Paper appeared in their flagship journal last year called Obesity, and also a paper this year in Management Science, joint with a Stanford PhD student, Yan Yang, and a medical school professor. So 1 out of 6 children in the United States is obese, and I'm not going to go through this, but lots of bad stuff happen when you're obese. The words they use in this field are universal and targeted, but the better words, more descriptive words, would be preventive versus treatment. So most of the action here is on the universal approach, or prevention, with First Lady Michelle Obama and Mayor Bloomberg leading the way, and there's a whole bunch of interesting stuff going on there. This paper is actually on the treatment aspect, on the targeted approach. Okay, so how do you measure obesity? Well, it's something called the body mass index, which is your weight divided by the square of your height. And the Center for Disease Control has these probability distributions for each age and each sex. And if you're over the 95th percentile of your BMI, over the 95th tail, then you're called obese. So it's a little bit like that, remember that old movie Spinal Tap, where the drugged out rock star puts the volume 11 on top of the 10 and says, well, it seems louder that way. So it's a little bit like this here. We have 17% of the children who exceed the 95th tail of the distribution. Okay, so there is treatment available here. It's very costly, very intensive, 25 hours of one-on-one treatment over a 6-month period, plus a diet component, plus an exercise component. And the U.S. Preventive Services Task Force, which is a group of medical experts, reversed their findings from 2005, and in 2010 looked at the literature and decided that this comprehensive treatment does indeed reduce BMI. And so they recommended that every child, when they go in for their annual checkup, or every 2 years when they go in, they check for obesity, and if they're obese, that they refer them to treatment. And another expert committee of 15 pediatric organizations actually recommended starting at age 2. So our research question here is, let's find the optimal screening policy and how suboptimal are these two proposed policies. So we're going to have a dynamic program here where the time stages are the age, starting at age 2 up to age 16. And the form of the policy we're going to focus on are BMI thresholds. So rather than always having it at the 95th percentile, we're going to choose optimal thresholds at each age. And the word deterministic in the title there is a little misleading because the state of the system is the population-wide probability density function of BMI. So it's an infinite dimensional, state space. And so we're viewing this problem from a societal point of view, not from an individual point of view, which of course is a much more difficult problem. Our objective is to minimize adult disease. The particular version we chose is based on the data that's available and subject to the fraction of people we refer to treatment, which you can kind of think of as a cost constraint. Okay, just a little bit about the model. So there's really 3 main elements of the model. The first part is, in the absence of treatment, how does BMI evolve? And we have data from sample pass of over 3,000 kids to look at that and find, because we're only looking at every 2 years, that it essentially looks pretty Markov, and after a transformation, the increments are normal, but this is non-stationary, so the normal parameters depend on the state you're in and the age you are. The next part is, how does treatment impact BMI? And that was easy because there was a literature review done for this task force a couple years ago. And the third part, which is really the hardest part, is how do you map from BMI into your objective function, which is adult disease? And there we needed 3 different databases that we had to kind of string together and then use logistic regression, and I won't go through that. Okay, so here's the main result. So again, we have a trade-off curve. The vertical axis is, I can't actually read it. What is the vertical axis? It's the disease prevalence. So we actually have 4 different versions. We have boys and girls, and we have hypertension and diabetes. So this one happens to be male hypertension, but they all look pretty similar. So of course we want the prevalence of adult disease on the vertical axis to be small, and then the horizontal axis is essentially cost, and we want that small. So we want to live near the origin. The 2 points above the curve, those are the 2 policies that are proposed by the task force. The left one is starting at age 6, the right one starting at age 2. And then there is our curve by solving the dynamic program for various values of the budget. And so the first thing we actually see is that this doesn't work so well. These curves are very flat. It takes 20 intensive 6-month, treatment regimens of children to avoid 1 case of adult disease. And also, the curve is not very convex, so that there's no obvious sweet spot that we'd want to be at. Also, the improvements are really quite modest. So if you go down vertically, so if you keep the cost the same and see how much can we reduce disease prevalence, it's 3% on a relative basis, is less than 1% on an absolute basis. If we go, horizontally to the left and say, okay, for the same health benefits, how much cheaper can we do it? It's a little bit bigger, 28%, but still. So more, the most interesting part here is, what is the optimal policy? So this gives the optimal policy. The vertical axis is the BMI threshold, and the percentile of the threshold, the percentile of the BMI, and then the horizontal axis is age. So the straight line going across, of course, is the task force recommendation that you always use the definition of obesity, which is the 95th percentile. Our optimal policy, essentially, what the punchline here is that children change their body shape when they go through puberty, and basically you want to wait till they go through puberty to do any of this testing. So in particular for boys, for the policy that has the same cost as the proposed policy by the task force, what you would do is go into every junior class of every high school in America and take over 50% of the boys, some of them who are not even overweight, never mind obese, and refer all of them to treatment. And that policy would actually do better, according to our model, than the proposed policy. So what we have here really is a negative result. So we found, I wrote diplomatically here, impractical, but really we have found a nonsensical policy that outperforms the task force policy. So in my view, really, the task force didn't really do its homework here. They kind of read the literature review, said, okay, BMI goes down a little bit from treatment, so let's start doing treatment. You know, they didn't look at all at the cost effectiveness, and this is, you know, fairly ineffective. And they didn't look at all, not even mention the supply side feasibility. This would refer 5 million kids per year to treatment. There's, you know, there's not enough, you know, psychologists or social workers, whoever, you know, does this one-on-one treatment to do this. So in our view, this money is better spent on prevention and, you know, give the money to the First Lady and Mayor Bloomberg and other people, you know, and just, you know, kind of spend it to get better food in schools and so forth. Okay, so in terms of impact, this is a negative result. It's kind of hard to implement a negative result. So, you know, we published in their main journal, and hopefully, you know, the leaders in this field have at least glanced at the paper. I sent the paper to Michelle Obama's staff, and I think they looked at it. I should go to their annual conference, and it just hasn't been convenient for me the last year or two, but maybe I'll go next year. But at this point, yeah, I mean, it is what it is, but it's not like there's any implementation to do here. Okay, so third problem is, you know, if you're like me and you don't watch TV cop shows, this might be the one problem where you have no idea what, you know, what's going on here. You know, you might not know anything about this problem. So first, this is joint with the same student and with two scientists who are in the National Police Headquarters of Israel. Paper just recently appeared in the Journal of Forensic Sciences. So when a gun is shot off at a crime scene, a cartridge casing comes popping out and lands, you know, on the ground. And these casings get particular scratches and marks on them as it gets ejected from the gun. And so what happens is that and here's the picture of what's called the breech face, or the back of the cartridge casing. So they take pictures of these and put them in a database. And then when you have a new crime and you get a new cartridge casing, you compare it to all the casings in the database. So the idea is that, you know, each unique gun might give scratchings that are maybe not unique, but are really quite characteristic. And so when you get a new crime and you get a new casing, you compare it to everything in the database, and if you get a hit, then that means there's a link between these two crimes. So for example, if you already know who did the most recent crime, you could charge them with, you know, other murders that happened in the past. And better yet, if you know, say pull someone over on the side of the road, they run a red light, you find a unlicensed gun in the glove compartment, you confiscate that gun, put a bullet in it, shoot it off, take a cartridge casing, compare it to the database, find, wow, this gun actually shot somebody, you know, 6 months ago. So you get a cold hit. Okay, so there's a national system in place for this. The acronym is called NIBIN. There's a single vendor from Canada, Forensic Technology, who does the software and hardware. It's used almost exclusively within state. They hardly ever do interstate searches, database searches, and it's quite honestly used quite inconsistently. I think some of the red states, just by principle, just won't use this. Okay, so, you know, what are we studying here? The main idea, the hypothesis here, is that crimes, and therefore crime guns, cluster in time and in space. And so, and also hypothesis is that evidence you get at a crime scene is kind of more suspicious than evidence you would find from a gun that wasn't at a crime scene. So our proposal is, when you calculate the similarity score, you know, between your new cartridge casing and something in the database, we're proposing a threshold system where the score is not, so you're taking account not just a constant threshold like this system runs now, but now the threshold is a function of how distant in space the new crime and the old crime was, and how distant in time the new crime and the old crime was, and whether it was from a crime scene or not. And so we're going to choose these thresholds, and when I say thresholds, I really mean these are functions of time and space and evidence or not evidence to maximize detection probability subject to false positive rate. In our longitudinal data here, it took us a while to get, but we got Israel's entire database and 3 years of arrivals and matches from them. And we used published performance curves from the company Forensic Technology, which almost surely are overestimates of the actual performance in the field. And then we loosely apply our model to cartridge casings in the United States. Okay, so research question is, is our hypothesis correct? Can we use the spatiotemporal information to actually improve system performance and solve more crimes? And could the US performance improve by doing more interstate searches? So here's the Israeli results. So this 93.1% here, this is their status quo policy, so they use a constant threshold system. They use a national search, so they, of course, it's a much smaller country. And so we find the detection probability is 93.1%. Okay. So of course, when you're starting that high, you're not going to get much of an improvement in detection probability, and we find our optimal, our optimal policy is 98.7%. However, when you look at it from a false negative rate, we actually resolve, over 80% of the false negatives. So this actually works quite well. We also did the counterfactual of if Israel just search within their own police precinct, they have about 70 police precincts, then the detection probably would drop to 73%. So that it's good that they're doing national searches. And of the 3 factors, we found the age, that is the time between the current crime and the one in the database, is the biggest factor, followed closely by the distance and space. And it turned out the evidence, non-evidence thing really was pretty minor. And thresholds kind of look like how you would expect them to look. Okay, so here's a rough application to the United States. This number in green, 87.3%, this is what they do now. So this is a constant threshold system that only does interstate searches. It turns out that the country is divided into 12 regions in terms of the databases. So a region is basically your state and the neighboring 3 states or something like that. And as you extend geographical coverage, there's a trade-off here. Of course, you're going to have the chance to capture something that's more distant, a gun that, caused a crime in New York and then came to Minnesota and caused a crime here. But on the other hand, the database gets much bigger, and this is really not very accurate. If you compare it to, say, fingerprinting or something, this ballistic imaging is much less accurate. And so the performance degrades as you get a bigger database. And so, in fact, we don't even have monotonic behavior here that, it starts at 87%, goes up to 89%, goes down to 82%. However, if you use our optimal policy, we can kind of bypass this trade-off and get up to 97% by doing a national search, but by setting the threshold very high for a distant search. And again, the false negative reduction is, over 75%. So I won't repeat this conclusion. I'll just kind of go to, what's happened since then. So there is an organization like Informs is an organization. There's an organization of ballistic imagers, and they have their own journal. Except I looked at the journal, and most of the papers are like 5 pages long. There's no math or anything. It just didn't seem possible to, send the paper there, so I sent it to Journal of Forensic Sciences instead. But they also have an annual conference like we do, and it happened last August, so I sent in the paper, hoping to go and give a talk there. And, I'm kind of waiting to hear, and it's like a month beforehand, so I emailed them back, and they said, no, your paper is rejected. You can't give it. They said, however, if you want, you can give a poster session. And I guess I was, too old or too proud or something, and decided not to go that route. But of course, my co-authors from Israel are, very much in the mainstream of this field. So they went to the conference. They told me afterward they talked to the organizers, and they said they were scared off by the math. But of course, I wasn't going to present, any math at the conference. So then I thought, what else can I do? And really, the only way, probably the best way I could possibly have an impact here is to send it directly to this company, Forensic Technology, who has a monopoly, on the market. So I sent it to them, and actually their vice president of technology wrote back and said, oh, wow, this is a really interesting idea, and thank you, I've shared it with all our scientists, and, that was that. So, I doubt they'll do anything with it. I also think if they did implement it in their software, I doubt they would tell me, so that's kind of where that stands. Okay, so, if you're like me at Informs talks, you kind of pay attention half the time. You pull out your book and see what talks you're going to this afternoon and things like that. So, in my view, this topic I'm going to talk about right here is the most interesting of the 5 topics. So if you're only going to pay attention for 10 minutes, I would say this is a good 10 minutes to pay attention. Of course, I should have told you that beforehand so you could have paced yourself. But okay, so this is joint with the same student and also with Jan Vandenbroek, who works in the field, nitty-gritty, got this big data set from Africa. And this paper appeared earlier this year in the Proceedings of the National Academy of Sciences. Okay, so here is a stark fact. In sub-Saharan Africa, 1 out of 8 children die before they're 5 years old. And it's been estimated that nearly half of that, 45% of that is simply due to undernutrition. Okay, so how do we measure undernutrition? It's a little bit like the BMI and obesity. So there's some similarities, the details are all different, but some similarities to the obesity problem. So here, instead of the CDC, the World Health Organization have these probability distributions for each age and each sex. And first, they measure weight for height. So it's a little bit like body mass index, but it's not that exactly. And it's a z-score, so, from a normal table. So it's telling you how many standard deviations, above or below the mean you are. So, and it turns out if you're more than 2 standard deviations below the mean in skinniness, it's called wasting. And if you're more than 3 standard deviations skinny, it's called severe wasting. And this is typically thought to be due to a transient food shortage or disease, just someone who hasn't eaten food for a long time. And it's also thought to be reversible. And about 9% of children in sub-Saharan Africa are wasted. And they also measure essentially how short you are, height for age. And if you're more than 2 standard deviations short, it's called stunting. And unlike wasting, stunting is thought to be due to chronic, kind of longer term, not as severe, but longer term undernutrition. And it's also thought to be much harder to reverse. And 38% of children in sub-Saharan Africa are stunted. Okay, so there is treatment. And there's something called ready-to-use therapeutic food. And the first and most famous of these is something called plumpy nut. And maybe you've seen, on 60 Minutes or on some TV show, seen something about this. So it comes in these little tin foil packets. It's a peanut base, so it's a little bit like peanut butter. And giving 500 kcals per day for 3 months, within a couple of weeks, this really takes these kids literally right off their deathbeds. And it really has revolutionized the treatment of severe wasting. And it's been so successful that they now use ready-to-use supplementary food. So it's the same thing, but just in lower doses to, kind of prevent extreme malnutrition and to treat more moderate forms of malnutrition. So it turns out there's really quite restricted funds here. So the estimate is that about 15% of these starving kids who need this food actually get it. And so NGOs and governments in Africa and elsewhere, have to make the decision, well, who does this scarce food go to? And they're really unsure how to do it. And so really the big research question in this paper and in several follow-on papers I'm be writing soon is, which children, based on their age, their sex, their height, and their weight, which children do you give the food to, and how much food do you give? Do you give, everyone a full dose, 500 kcals per day of plumpy nut, or do you cut the dose in half and give the food to twice as many kids? And so we compare our policies. So there are policies from USAID, that's part of the US government. They give more than half of the world's food aid, and also the UN's World Food Program. So they each have proposed policies. And so our approach is pretty similar. There's 3 parts of the model like there was in the obesity paper. And so the first part is, in the absence of treatment, how does these Z values for height and, for skinny and short, how do they evolve over time? And we have data from my co-author, over 5,000 children every 3 months. And it turns out with a 3-month interval, you actually need to keep some memory in the system. So we keep about 9 months of memory here. The second part, as before, is how does this treatment impact the height and the weight? And turns out that and I'll come back to this later, there's only one randomized clinical trial that has a treatment-free control group. It's really the only one we can use to estimate this, and so we do that. It's a paper that appeared in JAMA in 2009. And then the third part is, how do you map from height and weight into your objective function, which for us is going to be the disability-adjusted life years. And at least for deaths, we use logistic regression to do this. And in fact, one of the key points of the paper is that over 90% of the DALYs, or disability-adjusted life years, is actually due to childhood deaths. And this was interesting because in initial conversations with the World Food Program, they kind of thought, well, we've already solved with plumpy nut, this kind of severe wasting, and their biggest concern these days seems to be the long-term effects of stunting. And we found that this was kind of loose change compared to the childhood deaths, at least in sub-Saharan Africa. Okay, so I'm sure you can't read this, and I can't even see it from, right here on the slides, but these are our 7 benchmark policies from USAID and World Food Program. And I'll just comment that they're a combination of targeted policies. By targeted, I mean, for example, how skinny you are. If you're more than 3 standard deviations skinny, then we're going to give you the full dose of plumpy nut, and some blanket distribution. So an example is anyone under 2 years old who's between 2 and 3 standard deviations skinny, we're going to give half a dose of plumpy nut. And I should note here, I'll note it again, but the proposed policies by World Food Program and USAID only use how skinny you are. They don't use how short you are. Okay, so we come up with a rather simple policy, and because over 90% of the DALYs is due to childhood deaths, we simply use the logit argument in the logistic regression, and then we normalize it so it looks nice and simple. And so, for example, for girls, we give them a score which is 7.5 times how short they are, plus 8 times how skinny they are, plus their age in months. And then we just prioritize all the kids according to the scores. And then we actually, because it's hard to get a full-blown dynamic programming solution, we look at a 4-parameter policy where we're going to, every 3 months, put a kid into one of 3 buckets. The most severe kids are going to get the full-blown 500 kcals of plumpy nut. The ones in the medial level will get some medium dose. The ones in the lowest level will get some other dose, which could be 0. Okay, so here's our results. The vertical axis is, again, the disability-adjusted life years per child, so of course we want that small. The horizontal axis is the amount of cost per child. We want that small, so we want to live near the origin. So the red part is girls, the blue part is boys. Let's just focus on the boys for now, the blue part. So we have 7 little X's there that are up on near the top of the curve, and that's the performance of the 7 policies recommended by World Food Program and USAID. And so one thing we see is that none of those 7 policies are obviously dominated by the others, so that's good to see. The curve is kind of our optimized solution for every value of the constraint. And so, unlike the obesity thing, this actually works. It's actually, you may not be able to tell because you can't see the numbers on the axes, but, this actually works and you can do better. And the other thing is that this is not that flat a curve. There kind of is an obvious sweet spot where you might want to live. And so what are the reductions? Again, if we move down vertically and say for the same cost, how much can we reduce, basically childhood deaths? It's a 9% reduction. If we go horizontally and say for the same health outcomes, how much cheaper can we do it? We can do it 61% cheaper. So, these are somewhat modest, 9% is not huge, but just to put it in perspective, the Millennium Goals over a 15-year period, which are coming up in 2015, is to get a 2/3 reduction in childhood mortality. So that's 67%. And of course, this includes, bed nets and vaccines and, HIV and malaria and oral rehydration therapy and all kinds of stuff. So if you can get 9 out of the 67%, if these numbers are accurate, just simply by reallocating food, I would think Jeffrey Sachs or other people, who make these kind of, look at these things would think that's a nice, easy hit. The second thing that's interesting here is the optimal proposed policy. Again, we had 3 buckets with 3 dose levels. It turns out the optimal policy among that class is simply an all or nothing policy. So it's a rather ruthless policy where you just prioritize everyone. In the most severe cases, you give the full dose and everybody else goes home hungry. But I will point out that the existing policy, a lot of what they do is simply give Plumpy Nut to the kids who are more than 3 standard deviations skinny and don't give anything to anybody else. I mean, that's just as harsh a policy, it's just that we have a somewhat more sophisticated policy. Okay, so the 2 things I want to point out here. First one is the reason we're doing better is mostly that we're incorporating how skinny you are, whereas the current policies, we're incorporating how short you are, whereas the current policies only look at how skinny you are. And I don't have time to go through this, but what's going on here, I think, is that in the literature, people had looked at odds ratios in isolation, of odds ratios of HAZ and WHZ versus mortality. And because there's a certain asymmetry in the system, which is up there, but I'm not going to describe it, it turns out that these odds ratios give misleading results, and you really want to use a full-blown logistic regression to get a handle on this. And the second point, as I pointed out, is that right now there's kind of a big push towards blanket supplementary feeding, and we're saying that's actually not optimal. Okay, so where this stands, I think the paper was pretty well received. I went to USAID and presented there, and I think they kind of glazed over a little bit. And I presented at the Government Accountability Office too, because USAID spends a lot of money, on this. But it turns out the Tufts University Department of Nutrition is given a lot of money by USAID to look at these issues. And in fact, the USAID paper, the reference I give there to come up with these policies, is done by the people at Tufts. And so USAID sent the paper to Tufts without even telling me. It wasn't even published yet. And then I got an unsolicited email from the chair of the Department of Nutrition at Tufts and just said, oh, wow, your paper's been making the rounds here, and this is really great. We're so glad someone's finally bringing some rigor to this problem. So, we're hoping that that Department of Nutrition kind of is the conduit for impacting USAID and impacting policy. So just as far as next steps, because I'm spending much of the next year kind of looking at this, the weakest part of this study is the data on the impact of treatment. And as I said before, it's viewed, there's only one randomized controlled trial that has a treatment-free control group. 2 minutes? 2 minutes, okay. I think I'll just skip this, but we have interesting results on age dependence, and we're starting to study non-randomized trial and looking at data there. So I'm just going to give you a 2-minute version of this last problem. So India is undertaking the largest biometric program in the history of the world. For all 1.2 billion citizens, they're taking their 10 fingerprints and 2 iris images, and they're doing it for social inclusion so the slumdog millionaire families can get food and healthcare and stuff like that. And I think I will just go to the last slide here. It's unfortunate because all the results I gave you thus far are really quite modest, and these results are just, you know, spectacular in terms of the improvement. So this is a logarithmic scale, and so what we do is do an individualized policy. So for each kid, we're taking each person, we're taking a different subset of those 12, you know, 10 fingerprints and 2 iris images. And compared to what we're doing now, what the government is doing now of India, we get 100,000-fold reduction, so 100,000-fold reduction in the false rejection rate, which is when someone shows up who really is who they claim to be, and you tell them, no, you're not who they are. And the way we do this is for about a third of the people taking their irises, for about 2/3 of the people you take just fingerprints, usually one finger or a couple, and then for 1 or 2% of the people you take both of them. In UID, this is the name of the program, they're taking this quite seriously, and there's this guy maybe you have heard of who was the co-founder and former CEO of Infosys, and he was recruited into the Indian government at a cabinet level minister position solely to oversee this program. So he was briefed on our paper by other people in UID. In fact, they told us he even read the paper. And the last point is a little outdated, that the guy's trip to the Bay Area was canceled, but on this Thursday morning, I have a 2-hour Skype meeting to present these results to the chief of biometrics there. Okay, thank you.